made by the kinetic theory about ideal gases are: the volume of the gas molecules is negligible, and there is no intermolecular force of attraction or repulsion. The only two gases that behave almost ideally under room temperature and pressure are hydrogen and helium gas. Hydrogen and helium gases considered very light, so there is no intermolecular force between particles as they move at high speed. We know that all other gases also behave almost ideally when there is high temperature and given low pressure condition.
Gas behave like ideal gas. Then the PV tar RT is constant and equals to 1. This topic is important for STPM chemistry and often tested in theory questions.
Next, we will study the graph of PV over RT against pressure. We'll see how ideal gas shows positive or negative deviation.
In reality, gas molecules do attract each other and occupy space. Let's start with positive deviation from ideal gas behavior. Light gases like hydrogen and helium show positive deviation easily. At very high pressure, molecules are forced close together. The volume of gas becomes larger than predicted by the ideal gas equation. Positive deviation happens when repulsive forces dominate. So, the measured PV value is higher than the ideal value. We call it a positive deviation, which is PV RT more than 1. Consider as the gas deviates positively from ideal behavior. Carbon dioxide, ammonia, and methane gas. When PV/RT less than 1, the gas deviates negatively from ideal behavior. When pressure increases moderately, molecules become closer to each other, intermolecular hydrogen bonds form, and it shows negative deviation. The gas occupies less volume than predicted by the ideal model. As a result, the PV value is lower than expected. For real gas ammonia, intermolecular attraction dominates at moderate pressure, but at high pressure, repulsion dominates. Besides increase in pressure, lowering the temperature also can make an ideal gas deviates negatively. Molecules move slower, so intermolecular attraction becomes significant. This usually happens at low temperatures. In the next session, we will look at some questions related to this topic and hope this will help you.
First, you've got to meet our perfect suspect, the ideal gas. In theory, its molecules are just these tiny little points in space. They don't take up any room, they don't interact with each other at all, they follow the gas laws perfectly. So this is our baseline, our control group for this whole investigation. But here's the thing. In the real world, gas molecules aren't just points on a page. They've got size, they've got, personalities, and they definitely interact with each other. And that is where our mystery really begins, this whole deviation from that perfect ideal behavior. Right, let's open our first case file. We are investigating a diatomic gas, we'll just call it gas Q, and it's under interrogation at a blistering 650 Kelvin. So the big question is, why is it behaving the way it is? So, what's happening here? Well, when you squeeze these gas molecules really close together at high pressure, their own physical size suddenly matters a lot. They get all up in each other's personal space, and repulsive forces kick in, pushing them apart. This actually makes the total volume of the gas larger than our ideal theory would ever predict. And we can measure this deviation using something called the compressibility factor, or PV over RT. For a perfect ideal gas, it's always 1, but because the volume here is larger than ideal, that PV over RT value becomes greater than 1. And with that, case closed. Okay, so case 1 was all about repulsion at high temperatures, but what happens when we go to the other extreme? Let's open case file number 2. We're now looking at a different character, gas X, and the conditions are totally different. A chilly 180 Kelvin, and let me tell you, its behavior is way more complex. This gas is a real turncoat. As the pressure goes up, it doesn't just deviate positively. Nope. First, it actually dips below the ideal line. That's a negative deviation before it completely changes its mind and shoots way up into positive deviation. So what is causing this two-faced behavior? You can think of it like a two-act story. In Act 1, at lower pressures, the main characters on stage are the attractive forces between the molecules. They kind of pull the molecules together, which means they don't slam into the container walls as hard or as often. This makes the pressure drop below what we'd ideally predict. But then, Act 2. Just like in our first case, once that pressure gets high enough, those repulsive forces storm the stage and take over. The molecule's own volume becomes the star of the show, and the pressure just skyrockets. Rockets. So for our final case, we're presented with a lineup. We've got a graph showing the behavior of our mystery gas X right alongside a known substance, carbon dioxide, and of course, our ideal gas baseline. The challenge? We have to identify gas X. This graph right here, this gives us our key clue. Take a really close look. Both CO2 and gas X dip below the ideal line, so we know attractive forces are at play. But just notice how much deeper gas X takes a dive. That significant difference, that is our smoking gun. So based on that much more extreme dip, which of these suspects is our culprit? Is it neon, nitrogen, carbon monoxide, or sulfur dioxide? The answer is all about understanding what that dip really means. The evidence is crystal clear. A deeper negative deviation means the attractive forces between the molecules are way stronger, and you typically find stronger intermolecular forces in bigger, more complex molecules. So what we're looking for is the biggest molecule in our lineup. Let's compare the molecular sizes of our suspects. Sulfur dioxide is a significantly larger and more complex molecule than carbon dioxide, and it's definitely bigger than the others. This larger size creates stronger attractive forces between its molecules, which perfectly explains that deep dip on the graph. Our culprit has to be D, sulfur dioxide. So, after cracking all three of these cases, we can finally reveal the fundamental principle that's behind all real gas behavior. You see, it all boils down to a constant tug of war between two competing forces. And this is the key takeaway, for sure. On one side, you have intermolecular attraction. This is the dominant force at lower pressures and temperatures, and it pulls molecules together, causing that negative deviation. But on the other side, you've got the molecule's own volume and the repulsion that comes with it. This force takes over at high pressures, pushing everything apart and causing positive deviation. Every real gas is just living in the balance between these two forces. It's a really fair question to ask. I mean, if no gas is truly ideal, why do we even bother with the concept? Well, think of it this way. You have to understand the rules before you can really appreciate why they get broken. The ideal gas law gives us this perfect, clean baseline. It's a simple model that helps us get the fundamental relationships, and it's only by studying how and why real gases deviate from that model that we get a much deeper and honestly, a way more fascinating picture of how the world actually works. Makes you wonder, doesn't it? What other perfect scientific models have these amazing real-world exceptions? That's something to think about.
That's how real gases differ from ideal gases. You've got this. Thanks for your attention.